Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I just realized on the way over that since this is a continuation of yesterday's material, the actual definition of differential privacy doesn't show up in any of the slides. So it's here to remind you that for every database, every pair of databases, X and X prime, that differ only in that one of them is slightly larger and has the data of just one more person, the probability, the ratio of the probabilities of any event is essentially the same in each of these databases. It's bounded by e to the epsilon. Okay. All right. So here's a question. Can anybody answer why did we use a multiplicative notion for differential privacy rather than additive? Why did I want this ratio rather than a difference? So one proposal is that if we use multiple queries, it adds up. That's an interesting answer. It's not the one I had in mind. It's certainly a nice corollary of the fact that we did it this way. But I'm looking for something else. Well, what I didn't want is an additive notion, because remember that example that I said, people complain and they say, oh, really, don't worry about this. You know, it's only a few people whose data are going to be compromised. Well, suppose we have a mechanism which is the following. Whenever you have a database of n people, you just randomly pick one row and you publish the data for that row in its entirety. Your chance of getting selected is only 1 in n. It's not so bad. But for the person who's selected, it's absolutely terrible. That's what the multiplicative notion ensures. If you're not in the database, you could never have been chosen in that way. And that would put a 0 in the denominator here. So with this definition, we rule out randomly picking a row and publishing it. And that's a behavior that we wanted to make not allowable. So we defined it out of existence. Okay, one other question from yesterday. So let's suppose that we have a mechanism for answering a question that gives epsilon differential privacy, and we want to ask k questions. How do we do this in such a way that the total privacy loss is epsilon? What would we do to our mechanism? Remember that one of the mechanisms we used, let's say, for counting queries, was to add noise that was scaled to 1 over epsilon. What do I do in order to be sure that if I ask several queries, I end up with a total loss of epsilon? Exactly. I just use an epsilon prime here, which is 1 over k times epsilon. Then when I add them up, I get what I want. So the mechanism has the properties, they always have the property that you tell it what epsilon you want, it will ensure epsilon differential privacy. So if you have some total cumulative goal that you want to ensure, you can scale the epsilons down accordingly so that when they add up over time, we don't get past your target goal. All right? So what happens if you don't know the total number of questions in advance? What might you do?
First question we can answer with epsilon by 2, the next with epsilon by 4.
Exactly. You can play games like this. Blow half your budget on the first question, half your remaining budget on the next question, half your remaining budget on the third question, and so on. Okay, good. All right, so remember this from yesterday. we looked at these special queries called histogram queries, where the histogram query is you take the universe of possible people or possible data types, and you partition it into cells so that each possible person lives in only one cell. And the implicit question is, for each of these cells, how many people live in that cell? How many people in your database are in that cell? And this sounds like, if there are D cells, it sounds like D counting queries, but the total sensitivity of this query is just 1 because the presence or absence of one person in your database can change the count for only one cell, and that cell by only 1. So the sensitivity, that L1 sensitivity, is only 1. So we saw this yesterday, and I made this claim, that if epsilon is 1, then with probability 0.95, no estimate will be wrong by more than about 12.2. So the first thing I want to do now is the math for that statement. Where did that math come from? And the general thing that we're talking about now is what we'll call alpha beta accuracy for a set Q of queries. So remember yesterday, we started out thinking about sanitizing a data set. And we sort of immediately realized that we might run into some problems because we don't know in advance what all of the queries are going to be. A lot of the thinking today will involve a case where you happen to know all of the queries in advance. And you can think about the sensitivity of the entire query set. So a special case of that is the histogram, where in some sense you know in advance what all of the cells are, and you can handle the whole group of the counts for all those different cells all together and get a especially good outcome, sensitivity of only 1 rather than K. Now, what do I want to say? I'm going to introduce some notation that we're going to need later. We don't really need all of it today, but we'll need it in the next days, so we may as well start using it. I said that we assume that there's a universe of possible data types. We talked about that with the histogram query. I said there's a universe and you carve it into cells. For example, if each person in your database is described with, say, a D-bit attribute string, so 0, 1 of length D, there's a universe of size 2 to the D. So it's just the size of your data type universe. Okay, so I can think of a database as the database, not the query, the database as a histogram with U different cells. So here's the first data type, the second data type, the third, all the way up to U. And for each one of these, maybe I have, this many people of type 1 and this many people of type 2 and that many of type 3, nobody of type 4, and so on. And this is a perfectly reasonable representation of my database. And this ends up getting used sort of every now and then. A nice thing about this notation is it lets us easily talk about databases of different sizes. A database is simply a histogram over the universe of size U. So there are size of U cells. Okay. Now, when you have all of the queries in advance, and you're the curator, you have some options. One thing that you could do is you could compute the answers one way or another in some differentially private way to all of the queries, and you could release a long, long, long list. If this is the question you're interested in, this is the answer. If this is the question, this is the answer. And you could just go through the whole thing because you have the whole list of queries. Or you might publish something that's much more compact together with a little algorithm that says, okay, here's the algorithm, here's my compact data structure, and whenever you have a query, feed it to the algorithm with this compact data structure, and what you get will be an approximation to the answer for your database for this query on your database. One kind of compact data structure might be what's called a synthetic database. So it's something that looks a lot like a database. Maybe it's as big as your original database, or if you're lucky, maybe it's tiny and it has only a few people in it. And yet it's still a very good representative sample, so that for every query, if you apply it to this synthetic database and maybe multiply the result by some fixed number, you'll end up with a good approximation to the answer to the query on the original database. So we want to keep in mind the idea of a synthetic database, or more generally, just some kind of object, some sanitized blob that allows computation of the approximate answers to the questions. So that's what I have in mind in this bullet. So a mechanism M is alpha beta accurate with respect to a particular set of queries. So you can think now the queries are known in advance. If for every database, when I feed the database to my mechanism with probability all but beta, this thing that I release will allow the analyst to compute a good approximation to the value of the query on the database X. So what is a good approximation? It's something that's within an additive alpha bound. All right? So beta is going to be our probability of failure. With beta probability, absolutely no guarantees whatsoever. But with probability 1 minus beta, we're going to be accurate to within alpha. That's the definition of alpha beta accuracy for a set of queries. So it's a mechanism that allows you to ensure alpha beta accuracy. So now, fix the beta of your dreams. I don't know what it is, but just fix it. Choose one and fix it. It's supposed to represent an acceptable probability of failure. Once beta is fixed, what accuracy does the Laplace mechanism provide for, let's say, k queries? Okay? So we want to be a total of epsilon differentially private. So we're going to, as I erased, we're going to use a different epsilon prime for now, which is epsilon over k, the original epsilon over k. And we know that what we'll do is we'll add noise that's scaled to epsilon, to k over epsilon, to each of the query outcomes. And we're going to use this one fact, that when I plug in the parameter b to the Laplace distribution, the probability that I get something whose absolute value is at least t times b is exponentially small in t. Okay? That's the only fact that we're going to need. So again, we're going to have k random variables, because I'm using the Laplace mechanism with a privacy parameter of epsilon over k. So I'm doing this k times, one for each of my queries. So I'm going to have k random variables, each one distributed like Laplace with a parameter of k over epsilon. I'm going to allow a beta probability of failure. So I want to find t such that k times the probability that I'm at least t times k over epsilon in size is equal to beta. Why am I multiplying by k here? Well, it's just a union bound. Okay. So just do the arithmetic. Pull the k over to the right, so divide through by k. And I'm going to write that my probability of getting an answer that's at least t times k over epsilon is beta over k, which is e to the minus t. I'm going to declare that. So just doing the arithmetic, we see that t is the log of k over beta. All right? So if I plug in that value of t over here, I see that and I call the result alpha, I see that the probability that I'm going to have an error that's bigger than alpha is beta. So I will be alpha beta accurate. Okay? So that's where the math for that question came in. In a histogram query with k cells, we don't have sensitivity k, we only have sensitivity 1. So if we go back into that calculation, we see that the k's that are in blue are the ones that come from our sensitivity of the query set, which here is now 1 instead of k, which it would be for an arbitrary set of k queries. So this is the value that we would get, and that's exactly what we used in that slide about the number of names. We took epsilon equal to 1, k was 10,000, and beta was 0.05. Okay. Now, we used the histogram query to answer the question of what was the most popular name, or what was close to the most popular name. And it actually allowed us, at very low cost in terms of noise, to get the counts for each of the 10,000 names. Now I want to ask a different question. Instead of names, I'm going to talk about hobbies. Now, a person only has one first name, but they could have a very large number of hobbies. So my question, in the one sense, is going to look similar. Instead of asking, which is the most popular name, I'm going to ask, which is the most popular hobby? But it's not a histogram query anymore, because changing one person can change the counts of hobbies, many, many hobbies. So if we were using just the vanilla Laplace mechanism, the way we described earlier, we would release noisy counts for each of these things. And since, I don't know, maybe a person has 100 hobbies or 1,000 hobbies or 6 hobbies, whatever you think the maximum should be, that's what your sensitivity would be here. How can I get this down to 1? Sorry? Scaling by what? I don't know what the maximum is. In fact, my question is, what's the most popular hobby and how popular is it? So you're not supposed to know this, but I figured I would try. Here's a simple algorithm. It's called report noisy max. I'm going to first act as if I have a histogram query. So I'm going to add noise that looks like 1 over epsilon to each of the cells. But I'm not going to publish all those results. That would leak too much information. Instead, I'm going to add noise to each cell. I am going to, but I don't publish it yet. I'm the mechanism. I don't publish this yet. I then find the maximum number, the maximum noisy number, and I reveal that one. So let's say that the hobbies are, include knitting and playing the piano and playing soccer, or playing baseball. So maybe baseball has the biggest noisy count. After I add this noise, the number for baseball is the biggest. So I release to the public baseball, and here is the noisy number. So I'm reporting only the argmax and the maximum, and I do not reveal the other counts. The proof of privacy here is actually not very hard. It's a fairly straightforward case analysis, and it's your homework. So prove that this is differentially private, epsilon differentially private. Okay? Sorry. Now, we've been talking about counting. And implicitly in counting, when we think about numbers, we have in mind that for a given query and a given database, some numbers are really good outputs. Those are the ones that are very accurate, very close to the true answer. And some numbers are really bad answers. Those would be the ones that are inaccurate or far from the correct answer. And that our probability on outputs is going to drop exponentially as the quality falls off. That's what's going on in the Laplace mechanism. But there could be other notions of utility other than this kind of difference, exactly this difference. So we generalize to L1 norm, but you might have some other kind of notion of a good answer for a certain query on this database. It might be an L2 notion of error, more like a Euclidean a Euclidean notion of error, like in what Sanjeev was talking about yesterday. Or maybe the output of your algorithm isn't going to be a number. It's going to be a classifier that comes from applying a machine learning algorithm to the data. And what you want in real life, when you're not worrying even about privacy, is that your classifier should have what's called a good generalization error. So now maybe you would rank things according, the quality function would be how small is the generalization error. Small error, high quality. Big error, low quality. So you could have general notions of utility. And we'll see an example shortly. There could be cases where adding noise makes no sense. So for example, when I said you're choosing among a set of classifiers which one to release, you can't add noise to a classifier. I mean, here's the algorithm written in C. What does it mean to add noise to that? You want to choose from among a couple of different algorithms written in C. This is the best one for you. You can't add noise to something like that. Your output could be a string. It could be the name of a hobby. How do you add noise to the name of a hobby? What does it mean to say baseball plus 3? It doesn't mean anything. So in general, we're going to have a notion of a utility of an output. So when we look at a possible output, either it's a name of a hobby, it might be a real number, it might be a point in space, it might be a string. But for every database X, and for every possible output Y from our mechanism, we can talk intelligently about the utility of Y when the database is X. And that's what this notation U of XY is. The example that we're going to see later has to do with an auction. So the next technique is a very powerful technique. And it's exactly for the case that we've been discussing, where the output might be discrete, or for one reason or another, even if it's a real numbered output, adding noise won't make sense. And I will give you an example of that. So we have databases. And we have our function f. Our function might be find a good classifier, or it might be find the most popular hobby, or it might be find the best line or something. But let's say that we have a finite number of choices. And for each one, we have a utility. Some may have great utility. That means U of xy is large. Some might have small utility. Intuitively, what the exponential mechanism is going to do is it's going to assign a probability to each of these outputs. Rather, it's going to make a probability distribution, so the probabilities will sum to 1, for each of these outputs. Once it has done that, it then chooses from among these outputs with that probability distribution. So for example, if there are just 2 possible outputs, and one of them is much better than the other, the better one will have some big probability, the worse one will have a much smaller probability, and then we'll sort of flip a coin that's biased toward the big one with the appropriate probability. Okay? So again, the intuition is going to be that we're going to produce the output y from our set S with probability that's proportional to something that's exponential in the utility of y. And then, well, we always have this kind of epsilon stuff involved, and there's always some kind of sensitivity. So indeed, we're going to have what usually looks like epsilon over delta f. This is delta u. So what is delta u? I'm surprised I don't have it here. Delta u is, sorry. Anybody want to guess? What should the notion of sensitivity be here? It's going to be the maximum over all adjacent x and x prime and all y of the quality of y when the database is x minus the quality of y when the database is x prime. Oh, sorry. The utility, okay? So this is the sensitivity of the utility function. How much, in the worst case, can one person's data affect the utility? Okay. If you do this, then what happens when you have neighboring databases? Oh, well, what happens? I'm looking at this ratio of probabilities. I want to prove epsilon differential privacy. So I look at the ratio of these probabilities. This is the probability that I'll see y when the database is x, and this is the probability that I'll see it when I have the adjacent x prime. That's these terms, and then of course I have this guy, as usual. All right. So this is just a difference in the exponents, and we know by definition that this thing is bounded by delta u. That's exactly what that says over there on the board. So this goes away, and we get our epsilon, and we have e to the epsilon. So that's the intuition for the exponential mechanism. It's almost exactly what the mechanism is. There's a small caveat. And the caveat is this factor of 2 up here in the exponent. And here. So formally, this is because, yes, we assign probabilities proportional to something, but we also have to have a normalizing factor to make sure that the probabilities all sum to 1. And we end up paying, and when you do the arithmetic here, we end up paying a factor of 2 epsilon. So we pay epsilon over 2 for kind of privacy in the denominator and epsilon over 2 for privacy in the numerator, and we end up with a total cost of epsilon. So you should also work that out. Why is that? Why do we have that factor of 2? Show that that is correct. Now, the behavior here, if I were looking, say, at counting things the way we did for, actually, never mind what I just said. The behavior here is very similar to the behavior on report noisy max. I'll leave it at that. Okay. So there is an application of the exponential mechanism which really knocked my socks off. I thought it was one of the most beautiful things I had seen in years. So I'm going to tell you about that now. This is just a little bit of background on this slide for why it's an interesting why what I'm going to tell you is interesting. There's a relaxation of privacy that we'll talk about tomorrow that instead of promising that the privacy loss is always bounded by epsilon, says instead, well, with some probability of delta, there's just no guarantee. It could be arbitrary privacy loss. but with probability 1 minus delta, the privacy loss will be bounded by epsilon. So you can see that that's just a relaxation. And that's why I keep carrying around that 0 and saying epsilon 0 differential privacy. I want a delta equals 0. And there is a proof that we'll see tomorrow that shows that you can do actually much better than this k times epsilon privacy loss over k mechanisms when you relax to differential privacy. That k kind of gets transformed to something more like square root of k, which is great. So if you think about counting queries, what it will turn out to be the case is that you can get to almost n squared counting queries with epsilon delta differential privacy with an error for your counts that's non-trivial. I mean, I'm not promising that it's really good, but it's definitely sublinear. So, but those techniques die at that point. We can't do any better. We can't get up to n squared or n cubed, let alone 2 to the n over 6 or something queries. So the following result allows us to answer hugely many counting queries. And this is due to Blum-Liot-Roth. Can you all see, or is the font too small? You can see? Yeah? All right. So what they are going to do using the exponential mechanism is, given a database with n people in it and a set Q of counting queries, well, they're not quite counting queries, they're almost counting queries. Instead of saying how many people in the database have property P, we'll just change it to be a fractional thing. What fraction of people in the database satisfy property P? If you know the number of people in the database, you can go back and forth between the two easily. And using the Laplace mechanism, we can easily find out an approximation to the number of people in the database. So we'll use fractional queries whenever it's easier for us. And here's a case where it's going to be easier. So they're going to output a synthetic database. Remember, I told you what that was. That's something that sort of has the type of a database. And the answers to fractional queries on this synthetic database will be close to the answers to the fractional queries on the real database. So we're going to produce such a thing. For the exponential mechanism, we needed that set S, that finite set S of possibilities, of possible outputs. In this particular case, S is going to be the set of all small databases, where the definition of small, we'll get to later, is given by sampling error bounds, like from learning theory. And we're going to define, oh, I'm so sorry. No, this is right, okay. We're going to define the utility for Y. Remember now, Y is a small database. The utility for the small database Y on X to be the negative of the maximum error. So we look at all of the queries in the set Q. Remember that the mechanism has all of those queries in advance, so it knows what they are. For each one, it says, how big an error do I get for Q? When the database is X, if I'm thinking about the element, the possible small database to release Y, how bad can the error be? Now, utility is supposed to be a good thing. So if the error is, we want to put a minus sign to turn the error into a good thing. I mean, does somebody understand what I mean? So if the error is big, the utility is bad. If the error is small, the utility is good. So that's why we have the minus sign there. So that's how we get our utilities. And you can see that although it will take a long time to think about this and find the answer, the mechanism can indeed compute the utility for every single small database Y. Where remember, we have a bound on what small is, although I haven't told you what that bound is. But there are only a finite number of small databases because they all come from some, all data elements come from a universe U. So you could do that. So you can assign qualities to everything, utilities to everything. Now, what is going to be the sensitivity of an outcome of this utility function? So the query implicitly is what fraction of the people in the database have property P. So if I delete somebody from an n-node database, how much am I changing that utility? Only by 1 over n. Right? The fractional utility is the number of people who have the property, the number of people divided by n. The fractional query, Q of x, is the number of people in x that have the property Q divided by n. That's the fractional part. So if I take one person out, I'm changing this by only 1 over n. So that's my sensitivity. So now we could use report noisy max, or alternatively, we can use the exponential mechanism. And the exponential mechanism is how Blum-Liot-Roth did this. So for every y, we're assigning to y the probability that's proportional to e to the epsilon of the utility of y for x divided by 2 delta u. We assign those probabilities. That gives us a probability space. We sample. All right. So is it clear what they did? Here's a picture. Here are small databases, some utilities, and we took the maximum utility one. OK. Now, to understand how well it did, we're going to have to understand something about how big those databases are, those small databases are. We wanted we want some kind of alpha beta accuracy. So you can talk about what's called an alpha net. We have our set C of queries. And what we require in an alpha net is that somehow, if this big blue thing is the set of all possible databases, not all databases of a certain size, but all possible databases, that somehow every possible database is close to somebody in the net. How close? Alpha close. So for every database X, there is some y in the AlphaNet so that the fractional difference is bounded by alpha. That's what an AlphaNet is. Okay, so alpha says how close it promises to be. It's not going to be any worse than that.
So why some databases of X now? They're just arbitrary.
They're just arbitrary. It turns out they're just arbitrary. In fact, that's actually important. And here's an amazing fact that I'm not going to prove to you, although if there's great demand, we can discuss it in a problem session. For fractional queries, there is an AlphaNet that has that size. What is that size? This is the size of the universe. Remember, this is our universe of data types. This is what people can look like. And it's sets. We're looking at all of the sets of size log of the number of queries divided by alpha squared. So if we want a lot of accuracy, alpha is going to be very small. That exponent is going to go up. Okay. And the amazing thing is that this covers the set of all databases of any size. We're not restricted to covering databases of size n, just any size. So what this says is the set of all small databases of size log of c divided by alpha squared, that's what I mean now by a small database, the set of all small databases forms an alpha net. Now, notice that if an outcome y is good when the database is X, it'll be pretty good when the database is a neighboring X prime. There's not a whole lot of difference in the utility for neighboring databases. So we have our set of small databases. It's a database of size log of C over alpha squared. That's all. Notice that n doesn't appear anywhere in there. This is sort of universal. And it just depends on the query set. Yeah. So this will be the discrete set that we create the probability distribution on for the exponential mechanism. And so the question is, when you have a set of that size, what are we going to be able to say about the accuracy? Fundamentally, what are we going to be able to say about the accuracy? And it's going to take me a bit of work in order to get you ready to see the answer. Yeah?
So if you have an alphabet,
Yes.
then some qx and some qy are close to the
They're all, for every q, they're all close within alpha.
So if you have a mechanism which is alpha something accurate, alpha beta accurate, then when you are asking on a database, let's say X, you have with some probability you might answer for a different one, right? Because they are alpha close, and the alpha beta accuracy says that mx minus qx is bounded by alpha.
I'm not following the question.
So if you have an alpha beta accurate
Mechanism. Right.
means that probability that
I haven't promised yet that this is going to be alpha beta accurate.
I'm saying that if it is an alpha beta accurate, then instead of answering for this database, you might have answered for some other database.
I wouldn't think of it that way. What I would say is that if I have an alpha beta mechanism,
It's probably true that this thing is close within this alpha of some other database. Is that what you're saying?
it'll be within alpha of some nearby database, yes. But from an AlphaNet, we're not going to quite get alpha beta utility. We're going to get something like 2 alpha beta utility. And it's going to be a little bit worse. Okay? All right. So forget about the application for a minute. We're just going to look back at the exponential mechanism and say, what do we know about it? In general, what can we prove about it?
Can I ask a question from the previous slide? We saw that there exists an alpha net of small size.
Yeah.
But how do we, from there, how do we argue that the small databases themselves form an alpha net?
Actually, what I wrote here, oh, I'm sorry. You're right. What I should have said was not only that there is an AlphaNet of that size, but in fact, the small databases is such a thing. You're absolutely right. My mistake. Okay. Okay. So we've sort of popped back up a level, and we're looking now at the exponential mechanism in general. Our set capital Y is going to be the set of all of the possible outputs from our mechanism. So in this particular example, it would have been all possible small databases. Some subset, when I have a database X, some subset of Y is optimal. Among the guys in Y, some subset is the best that you could do. So Y star is going to be the set of these optimal utility outputs. So U of X, Y star is optimal, and that optimal value is called U star, and this will hold for every Y star in capital Y star. All right? So there's going to be at least one optimal output. That means that this denominator will always be at least 1. All right. So the theorem says that if we look at what is produced by the exponential mechanism when the database is x, and that's m sub e of x. So we run the thing, it assigns its probabilities, it picks an output. That output has some utility for x. What is the probability over those coin flips that this utility is at most v for any particular number v? The claim is, which will have a very simple proof, that this probability, that the utility will be bounded by v, is at most this expression. So let's see why that's true. For the numerator, suppose the utility of y is bounded by v. U of xy is at most v. Then we know that before normalization, the unnormalized weight of y will be it will be at most e to the epsilon v divided by 2 times delta u. Because remember, we assigned a probability that was sort of proportional to how good something is. We put in the exponent how good something is. So the probability is proportional to e to the goodness. The goodness is at most v, so the probability will be at most e to the v with these other epsilon over 2 delta u things that we have to carry around for privacy. And there are at most y such elements because y is the size of all possible outputs. So clearly there will be at most y such elements. How about optimal elements? Well, same calculation. Only their utility will be at least this much. In fact, it'll be sort of proportional to exactly this. That's how it's assigned, right? You're assigned probability that's proportional to e to your utility. Your utility is u star because this is an optimal one. Okay? And there are, well, however many optimal there are of those. So that's our y star. However many optimal there are, it's at least 1 times the utility of those. Okay? And now everything works out beautifully. We have the y over y star from here. And we just have this, v minus u star over here. Well, is this good or is this bad? I don't know. Does it look good? Does it look bad? It's hard to say. What's going on here is, okay, we want this number to be small. If v is less than u star, we want this number to be small. What's making it big? What's making it big is this term. All right? What's making it small? V is smaller than u star. This quantity is negative. The smaller v is, the exponentially faster this term is becoming small. So the y over y star term is fighting with the drop that's exponential in the drop in utility. And that feels like a good thing. It is a good thing. And an immediate corollary will be this statement. It says that for this messy-looking expression over here, this stuff all comes from the privacy. So, and this you saw over y star. So what it's saying is the probability that you're going to be sort of from here to here away from optimal is bounded by e to the minus t. Yes?
Can you please come to the
Previous slide.
So you're just taking that term, v minus u star.
Exactly. Exactly. And in fact, that is the proof. So from the previous slide, we have this. And now I'm taking that expression in green and I'm plugging it in here for the green V. So you were exactly on target. And that's the proof. You just plug that value in, do the arithmetic, and you'll verify that you get a bound of e to the minus t. That's simple. Okay, so this is what we know about the exponential mechanism in general. That under good circumstances, if the cardinality of y isn't way too much bigger than the cardinality of y star, you're going to do well. It turns out that when you take this and you put it in a meat grinder that tells you the bound on the size of the AlphaNet, this is where we used the bound on the size rather than which strings it was, we end up being able to conclude 2 alpha beta accuracy for that small database thing. So the only thing that I want to point out a couple of things here. Don't worry about the log beta term, that's always there. It floats around with us forever. What we're getting here is log of the number of queries, log of the universe, and alpha squared in the denominator. And there's this thing that comes from the sensitivity. Remember the sensitivity was 1 over n? So that's why we have an n here in the denominator. When you take all of this and you chug on it, if you just look at the dependence in n, you end up being able to show that for true counting queries, not fractional counting queries, but true counting queries, so you multiply through by n, you get a dependence on n for your error that looks like n to the 2/3. Yesterday, we were looking at errors for counting queries that looked more like n to the 1/2. So they were better in terms of their dependence on n. Here, by sacrificing a bit in the dependence on n, we were able, and using really wonderful technology, they were able to go much, much, much farther. Okay. Good. And when you can play with this for a bit, and see that we really can handle more than a polynomial number of queries for if the other parameters behave nicely, if the universe isn't too large, for example. And still have epsilon 0 differential privacy. How about the computation? It's insane. And there, in fact, you can show that under cryptographic assumptions, there's no efficient method of doing this. All right. Going back to the easier question, most popular hobby, plugging in the bounds that we just got for the utility of the exponential mechanism. We get this expression. And here's an example. If we take epsilon equal to 1, then if the most popular is, say, 50 more popular than the next most popular, the second most popular, the chance of not selecting it will be e to the minus 15. You can prove things like this. So the key point here is adding or deleting one individual can change the score of the most popular hobby by at most 1. And that's changing the score of the most popular, as opposed to what happens when we look at sort of the vector of counts for the popularity of each of the hobbies. Adding or deleting one individual can affect the score of, maybe all of the hobbies. And this is what gets to be exploited in the exponential mechanism. All right. You can also use the arithmetic that you have already seen to bound the expectation. So for any v, we had this bound on the probability that the utility would be at most v. So you could multiply v times the probability of such an output to get a lower bound on utility. And McSherry and Talwar used this to bound the revenue from a differentially private auction for digital goods. And we'll talk about that next. So I'm not going to say a whole lot about this because, one, it's a field very, very much that has more open questions than resolved questions. And two, I'm not an expert in it. So I'm not the best person to talk to about it. But in an algorithm, in some sense, we have the data. The algorithm has the data, and we control everything, so we can just design the algorithm. But in auctions and game theory and things like this, you want to design the constraints and the incentives so that the people who are taking part in your auction or taking part in the game will behave the way you want them to. Specifically in auctions, you want to model the incentives of people who are assumed, first of all, to be rational. That is, they can think through the consequences of their choices. And that they're self-interested. They have some notion of what's good for me, and they're only trying to increase their goodness, their happiness. And we want to model the incentives to shape their behavior. And design the rules of the game when we have these rational, self-interested agents. We want to design the rules of the game to shape their behavior. So you can make a relationship to privacy that looks as follows. When you're designing an auction, the input data belongs to the people who are taking part in the auction, the ones who are placing bids. In private algorithm design, the input data belong to the people in your database, right? Now, when you're designing an auction, individuals have a subjective perception of the outcome, which is their notion of utility of the outcome. I want the apple. I succeeded in buying the apple. That has a certain amount of utility for me. I failed to buy the apple. That has less utility for me because I'm hungry and I want the apple. In private algorithm design, our notion of cost is a little bit more amorphous. Somehow it's, gee, how bad is it for me if my privacy loss is epsilon, or maybe if it's 2 epsilon? You know, is that a lot worse for me, a little worse for me? I don't know, but there is some kind of intuitive notion of the cost to me as a function of the outcome or the consequences of the outcome. In mechanism design, people who are designing auctions, for example, it's well understood by people who really understand these things that you have to design the rules of the game to get people to participate. In the private algorithm design, well, yes or no. I mean, we talked about the whole point of the definition of differential privacy being to encourage people to allow their data to be used for socially good causes, like medical research. So maybe you have to incentivize individuals. Now, I'm not going to go further into that analogy, but I will give you a pointer shortly. The principal application that McSherry and Talwar spoke about in their paper was what are called unlimited supply auctions. So they have this incredibly powerful tool whose power was, I think, you know, maybe they understood it, but certainly when Blum-Liot-Roth did that small database thing, everybody saw it. But they were thinking about auctions. So in an unlimited supply auction, the person who's selling really has an unlimited supply of something. So the more people want, the more the seller is able to sell. So an example of this would be a digital good. It costs essentially nothing to make a copy of the software and sell it. So there's an unlimited supply. And bidders have demand curves. So if we're going to, let's say, fix prices to be in an interval between 0 and 1, for every individual eye participating in this auction, and for every price P, they have a demand. They want BI of P items at that price. If apples are cheap, I want a lot of them. If apples are expensive, maybe I still want one, but I don't want two. So the only requirement here, I guess, is that it should not be decreasing. If it gets more expensive, people have to want less. No, they can't want more. Now, the auctioneer is going to choose a fixed price in order to optimize its revenue, how much the seller is going to take in revenue. What is that? That's the sum over all the price. When the price is fixed at P, the seller will get the sum over all of the bidders of how many P times how many items the ith bidder wanted at that price P. Okay. So if we let U star denote the optimal revenue for a database of bids, the idea is we want to select the price using the exponential mechanism. That was their motivation. Now, what was wrong with the old Laplace thing where you would just compute the best price and add noise to it? Suggestions? Well, oh, by the way, yesterday we mentioned Dinur and Nissim and McSherry and Talwar and Smith. Okay. So, suppose Dinur and Nissim and McSherry and Talwar are each willing to pay $1 for a pumpkin. And Smith, for some reason, is willing to pay $4.01. Okay, what's the best price? What maximizes revenue? 4.01, right? So let's say we take 4.01 and we add a little noise to it. If the noise is negative, and we come up with, say, $3.99, what's the profit going to be? If the price is set at $3.99 and somebody is willing to spend up to $4.01, what's the profit going to be? $3.99. Right? The other people aren't willing to pay $3.99. So that's not so bad. But what if the noise were positive and the noisy answer was 4.01? What would the revenue be? 4.02. What would the revenue be? 0. No one's willing to spend $4.02 for a pumpkin. So these very little differences have huge impacts on the utility of the price for this database of bids. So you don't really want to choose according to how far you are from the optimal price. You want to choose in terms of how far your utility is from the optimal price. And that was the motivation for the exponential mechanism. Here's a question. What do we need in order to safely use the exponential mechanism? We have to figure out, well, the set of possible prices. Look at these bids. What's the set of possible prices? What? 4.01? 1 through 4.01? Any other takers? This is a trap. You cannot have the set of possible prices depend on the bid. You have to fix the set of possible prices in advance. What if I have two adjacent databases and 4.01 would be a possible price on this one and not a possible price on its neighbor? Then you would have something that has non-zero probability here and 0 probability on the neighbor. Not acceptable. We won't get a ratio like this. We'll have a 0 in the denominator. So keep that in mind. In the situation that we were just describing, here, I very carefully said, the price is in this interval. Okay. All right. This is a kind of thing that you have to watch out for all the time in privacy. You can't have somehow your mechanism itself depend on the database. You have to separate those two. Okay. All right, so we explained the motivation for the exponential mechanism, and we analyzed it. And here's a couple of consequences. First of all, you get a mechanism which is, you get an auction which is approximately truthful. And it has another property, which is collusion resilience. So approximately truthful says an individual can't substantially affect the outcome by changing her bid. And that comes basically for free from differential privacy. And it's very close in statement to what people who do auction theory talk about with approximate truthfulness. So what this seems to say is that the bidder sort of may as well be truthful, tell her true utility, give her true supply curve, demand curve, because she doesn't have a whole lot to gain from changing it, which is kind of encouraging, except for the fact that she also doesn't have a lot to lose for lying. And so there's a little literature around what do you do about this fact. And again, I'm not an expert in it, but I'll give you a pointer in a moment. Another thing, remember that differential privacy, if you have epsilon 0 differential privacy, then for groups of size k, you automatically have k epsilon 0 differential privacy for your group. So what that means is that a little group of colluding people in the auction can't substantially change the prices. And apparently, and I keep saying I'm not an expert, but apparently collusion resilience in auctions, people didn't have really strong or robust methods for achieving it. That's my understanding. So this was, as I understand it, considered a very interesting contribution, and it followed immediately from the properties of differential privacy.
Sorry, why does collusion resistance follow? Can you say?
Oh, because if it's epsilon 0 differentially private, then for a group of size 2, it's going to be 2 epsilon 0 differentially private. That means that two people working together can't really affect the probability distribution on outputs very much. So you get collusion to groups of size 2. And you get slightly worse collusion to groups of size 3 and 4 and so on. Okay? So for the same reason that it's approximately truthful for 1, it's approximately truthful for 2 and 3. And that means that even colluding, they can't make much difference. Now, there is a wonderful, wonderful tutorial by Aaron Roth on the DIMAX website. I've given the URL here. And he talks about this connection between mechanism auctions and differential privacy and some of the research directions and what's been done. And you will see some of the slides that I used in that tutorial. I got them from him. Okay, now we saw that this amazing application of the exponential mechanism, or report noisy max, allowed us to amazingly increase the number of queries that we were able to answer with non-trivial error in a differentially private way. And when I, who had been playing with these sort of up to n squared queries, saw this exponential in n number of queries, I couldn't understand. Why was it possible? So how was this possible? Well, for one thing, historically, we were very interested in errors for counting queries that were little o of square root n. Why? Well, remember that we said when you sample from the population and form your database, if you're trying to understand what fraction of the population as a whole has a property p, you're going to have errors that look like square root of n, or when you divide through by the size of the database, 1 over square root of n. All right? So we wanted privacy to come for free and not give you any more distortion than your sampling error was giving you. And that was true in the earliest results, which you actually haven't even seen, even like in sort of proto-differential privacy land. And we thought that's what made it really interesting, was that we were below the sampling error. And we didn't even think of being as evil as having counting errors on the order of n to the 2/3. So one of the things that happened was Blum-Liot-Roth not having come from our particular line of thinking, they didn't care about this difference between square root of n and n to the 2/3, so they were happy with that, and good for them. You know, it was great. So there was this historical blinders that were on us. That's one reason. Now, what about kind of a more serious question of how was it possible? Well, is it because all of the queries were known in advance? I mean, we really, really used this in choosing our utilities. Right? We knew all of the queries. We could assign a utility according to the maximum error. No, that isn't it. And in fact, you can get similar bounds in an online fashion. So the queries come, you give an answer, the next query comes, you give an answer, the next query comes, you give an answer, and so on. And this was done in two works, Roth and Roughgarden, and Hart and Rothblum. So you don't need to know the queries in advance to get this fabulous behavior. And was it really the n to the 2/3 being bigger than 2, like opening the minds to the n to the 2/3? Well, maybe, but it's even possible to get something like a dependence of square root of n times some polynomial in log of n dependence. And that's work with Naor, Reingold, Rothblum, and Vadan. What about the fact that the responses that are given by the mechanism to different queries are coordinated with each other? With the Laplace mechanism, you come, you ask me a question, I compute the answer, I choose independently generated noise, I add it, I give you this. You bring me the next question, I do the same thing, independent of everything that I've done in the past. So those are completely uncoordinated answers. But in the algorithms that achieve these bounds, things are coordinated. Is that necessary for achieving this kind of power? And the answer is yes. And this is work with Naor and Vadan. So let's just, in the last couple of minutes, let's just talk a little bit about how that argument goes. So you can formalize this question by saying, what can you do with a mechanism that has no state? It doesn't remember what it's done before, right? Answers to subsequent queries do not depend on answers to previous queries or what previous queries were asked. So one way of formalizing this is kind of to say, well, how distributed can I make everything? So what I'm going to do is this. We have our initial database. I'm going to choose some incredibly long string of random bits, as many as I need. And I'm going to ship to remote corners of the world this random string. So here's a mechanism that's in Beijing. Here's one that's in Hyderabad, and so on and so forth. And these things won't talk to each other. And each of them will only answer one query and then turn itself off. That's as uncoordinated as it gets, right? OK. So somebody comes along, asks the first query, this mechanism with the database and the query and the random string gives a response, and so on and so forth. But they don't talk to each other. They shared some initial state, and that was that. OK? Yes?
R's are all the same?
They're all the same. Doesn't really matter. I said R could be really, really long. So we could dedicate one chunk If we wish, we don't have to. All right. And this is going to answer some number t of queries, big number of queries. So what are some examples of stateless mechanisms? One, we've talked about it already several times, adding independent noise. That's stateless, and it has non-trivial accuracy for some number just a bit less than n squared of queries. Another is randomized response, which we saw yesterday for a binary output space. And here we've generalized it. So, sorry. Everywhere else I've been using X to be the whole database. Here, X is an element in the database. My apologies. So either you stay where you were with probability epsilon over the size of the universe, or you choose randomly from the universe otherwise. And this turns out to be accurate if the universe isn't too big. Now, another is what we call the density response. Ignore the query. If you want to know what fraction of the people in the database have a certain property, I'm going to ignore, not ignore the query, ignore the database. I'm just going to say, well, what fraction of the universe, period, has this property? And if somehow the query is independent of the actual database, chosen without knowledge of the database, then most of the time you're going to get a perfectly accurate answer because somehow your database is going to be representative of your universe. All right. However, you can't go beyond that. So the theorem is that there is no stateless differentially private mechanism that can answer more than n squared times the log of the universe queries. We know that we can get almost up to n squared queries using independent random noise. This is kind of a tight counterpart to that. We can't go much worse than that, provided the universe is of size at least bigger than n squared. Now, one interpretation of this is that if we want to answer a lot of queries, we can't 100% completely distribute the work of responding to the queries. Okay? So you can't completely distribute. Later, we'll see a second interpretation. And in fact, it'd be very interesting if you can come up with the second interpretation on your own. So think of another interpretation of this. I've given you all of the hints you need. And I'm just going to say a couple of words about the proof. Yes? Well, I said what it meant, that one interpretation of being stateless is that we do some initial thinking about stuff. We send it off to the different servers, and we never let the servers talk to each other. Yeah, right. They have to answer stuff on their own steam, and each one can answer just one question, and then it quits. And that's completely independent. It's completely distributed. Okay. All right. So the answer involves what's called a hybrid argument, which some of you may know from cryptography. We have our universe. Uh-oh. Sorry, we just have notation battles, and it's my fault. All right. We have our universe, U. We have our database, which is supposed to be a subset of U, not capital X. That was an X that I failed to get rid of. All right? My database is going to be a subset, not a multiset. So it may have n elements, but they'll all be distinct. Okay? We're going to define a query to also be a subset of the universe. And the semantics are, what is the size of the intersection? So maybe my database has the people in this room. And the queries, the query is the authors of the PCP theorem. What is the intersection? What is the size of the intersection? It is 1. Okay? So that's what the queries are. So if my database is of size n, then there are only n plus 1 possible answers to the query, right? The intersection could be 0, could be empty. It could be 1 person, 2 people, 3 people, up to n, and that's it. So those are the possible sizes or outcomes that could be delivered. Now, if our thing is going, if our mechanism is, reasonably accurate in any sense, then when the intersection is empty, this thing is supposed to give an answer that's close to 0. It doesn't have to be exactly 0, but it certainly shouldn't look like n over 2. When the intersection is actually of size n, that is, when the database is completely contained in the query, we should get an answer that looks something like n. Doesn't have to be exactly n, but it shouldn't look like n over 2 or 0. All right? So that's a requirement from accuracy. And if we think about these as fractional queries, then instead of having an n there, we'll have a 1. Okay. By the way, just to help your thinking, there are no rules about this mechanism. It can do whatever it wants as long as it's going to be differentially private and be relatively accurate. So for example, every time Sanjeev is in the database, it could decide to ignore him. Just pretend he's not there. It's not going to change the answers by very much. But kind of no matter how many times you ask about Sanjeev, it's always going to pretend he's not there. It's okay. Could pretend, well, okay. Nonetheless, when the intersection is empty, it has to be close to 0. When the intersection is of size n, the answer has to be close to n. So somewhere in there, there's going to be a pair of sizes where when the intersection is of size k minus 1, the answer will look kind of a little bit smaller than when the answer is of size k. In some expected sense. In other words, even though my mechanism might choose to ignore Sanjeev, it can't ignore everybody who's in the database. Somewhere it has to behave a little bit differently if that person is there or not there. So we get a gap. And now the strategy is going to be, the strategy for the proof is going to look like this. We're going to, we who are running the proof, are going to choose an element psi from the universe. And then we're going to choose n minus 1 other elements, psi complement. And we're going to hand to the adversary psi complement. Just give it to him. So now this guy knows almost the whole database. But there's one guy in the database he doesn't know. And his whole job in life is to try to guess who is that last person in the database. The universe is big, so if he guesses at random, he's very likely to be wrong. So he has to do something smarter than just plain guessing at random. What's he going to do? Well, remember, we saw on the previous slide is that somewhere, when, there has to be some kind of difference between the case when the answer is k minus 1 and the case when the answer is k. For some k between 0 and n, 1 and n. So the adversary doesn't know this mechanism, but he knows there is some such k. There are only n choices for it, so he picks one. He guesses one at random. Having done that, he's hoping that this is a place where there's going to, a gap is going to be revealed. If it isn't such a place, he loses. All right? But it might be such a place. In fact, with probability 1 over n, at least, it's such a place. So let's say that he's lucky, he guessed such a place. Now what he's going to do, which he will do whether he's lucky or not, because he doesn't yet know, is he's going to compose a bunch of random queries. Each random query is going to have the property that he knows about, that the intersection with the part of the database he knows is k-1. He doesn't know that last element of the database. So if the last element in the database is in his randomly chosen query, the true answer is k. If that last element in the database is not, the true answer will be k-1. And all he does is he makes up a whole bunch of these things, and he asks them, and he just kind of looks at the answers and tries to figure out, are we closer to the k world or closer to the k-1? Am I getting more, no, sorry. No, I said that wrong. So he asks a bunch of queries like that, something like n squared, a little bit more than n squared queries like that. And then he does some thinking. And the key point is that the responses will be detectably correlated with what's called the dictator function chi of xi, which is a function that's sort of 1 when xi is in the database and 0 when it isn't. And this detectable correlation is sort of in expectation, and it would be detected over many queries. So that one part of the proof shows that there will be a correlation, and of course your intuition should say, yeah, there will be, because when it's there, you're going to get a higher value. When it's not there, you should be getting a lower value. The problem is, well, never mind. Okay. The other thing that's proved is that the responses are correlated with very few other elements, very few people who aren't in the database. I said that the mechanism can act weird, and when Sanjeev is there, he pretends he's not. A different mechanism misses Sanjeev, and even when he's not there, he pretends he is there. So then the answers would be sort of erroneously correlated with Sanjeev, which is just ridiculous. But there won't be too many people that he can do that for. So that's the general strategy for the proof. Now, this is a very powerful technique. And I believe that if we go back and remember that genome-wide association study that we talked about where what were being released were allele frequencies for the different SNPs. I think that what's going on at the heart of that is in fact this kind of argument. That it's actually, I mean, of course they didn't frame it in these terms, but it's, I think, the same thing. I think morally the same thing is going on. And so I said, if you've been doing these things for a while, when you saw the Homer et al. Result, you say, well, of course. And it's kind of like that. Okay. So again, the first interpretation of this result is that you have limited parallelization. And that's the end for lecture 2. Yeah, good. Okay. Questions? More questions?